Let's look at another sequential allocation model. We will see that in this model we don't have uncertainty, and later we can introduce uncertainty at different places. So let's go over the assumptions first. Again, we have a total amount of fortune A for investment in n periods. So we have the same structure. If we sketch a diagram, we have n periods, and you can think about this is period 1, it's like today, and then this is going to be future. We always have this kind of structure. And try to see what kind of action variable we have, decisionally again, based on our experience that we say action variables are usually easier to identify. And what we have is the size of investment each day. Size of investment. Let's call it still y. During the first period, y has to be less than or equal to capital A. But in subsequent periods, we still need to know how much is still left for us to invest. So we cannot really use capital A all the time, so we better introduce another variable for the amount of fortune that's available to us to invest. So that's going to be our state variable, how much available, state variable. This is still very close to the gambling model. So we have amount available, resource available, you can say, and let's say X. Okay. Initially it's capital A, right? So now after we do this, we try to calculate what's going to be the return if we invest Y for today, and then we add the expected maximum return from the future. The future over here, we don't know for certain, so it's going to be expected. Okay. And for today, we need to now make an assumption that we're going to invest. It's not optimal yet, so let's just say invest Y. And X is the amount available. So what do we have over here? Determine the range of Y. Y is between X and 0. This is 1. If we invest Y, then today's return is going to be R of Y according to our assumption. And then plus future. Expected value of future, because there is no uncertainty, so we know that for the future we have X minus Y left, and that's going to be for the future. Now, before we can write down the formula, we need to actually first have the V variable, the optimal one. So we now write down over here Vn of X. What's going to be this? That's going to be the optimal, even though we don't have uncertainty, let's still say expected, because anyway, we can say the probability is 1. Optimal expected return, the total return from all n periods, and with current asset or current fortune, with current amount of fortune, X. Or you can say at the very beginning is capital A over here, right? So now what do? We can say if we invest Y today, then we have the total return ry for today, and plus the maximum future, that's going to be v n minus 1, because now we have only n minus 1 periods left. And because we have invested y, and any return on this y is not available for reinvestment, so what we have now left is capital A minus y. That's how much we have left. And there is only one state variable over here. And then we maximize over y. So we now then maximize over y and make sure you know the range of y. And that's going to be, if we use capital A, then we just use capital A. If we use x, it's going to be just x. So A over here is simply x, right? And then greater than or equal to 0, and ry, and plus vn minus y, and x minus y. And we can still see the structure of today's return plus best of the future. And then maximize over only one variable, which is today. And that's the structure of sequential allocation, Bellman equation. And this is our Bellman equation. Now let's try to see if we are given that r of y is root y, how can we solve this problem? So we start from v1. So v1 of y, v1 of a is going to be the maximum, and y is between a and 0. And then we have ry. Remember, there's no future, so any leftover is 0. So we say it's no value to the leftover. Okay. If there is any value to the leftover, we put it over here. Now, if you look at this function, we have the maximum y less than or equal to a, bigger than or equal to 0. In fact, as long as r is an increasing function, we know the maximum value is reached at the right end point. So here is just a special example, and we just take square root of a. Invest everything. You can see this is invest everything. Invest everything. Right? So this is v1. And once we have v1, we can find v2. So v2 of a, let's say we start with amount of a, and then we maximize over today's action how much to invest over today. And if we invest y, that's the return for today. And the future, then this is already optimized, so it's v1, but now we do have a minus y over here. Okay, so that's what we have. So now let's plug in the formula. We already know v1, so this is going to be the maximum y less than or equal to a, bigger than or equal to 0, and root y, and plus square root of a minus y. Again, we have a problem of calculus. We maximize a function over closed interval and with the parameter a inside. So we do the calculus on the side. So let's say we call this function f of y, and that's going to be root y plus square root a minus y. And we want to find that maximum value. So we find candidates, find first, takes derivative, find first order condition. Takes derivative, we have 1/2 1 over root y. And be careful about the chain rule. The second one we're going to have negative because of chain rule, 1 over a minus y. And because of this negative y. And set this to 0. Based on our experience, we can say now we have this equation. Right? Square both sides, we have a minus y. Or multiply cross product, we have y over here. And then we have 2y is equal to a, and y is equal to half of a. If we take one more derivative, we know this is going to be maximum. Take second order derivative of y, and then we will have negative 1/4 y, negative 1/2 minus 1 is going to be negative 3/2, and then take the derivative of the next one. We have again a negative 1/4 and we have a minus y to the negative 3/3. Remember the chain rule, we have three negative signs over here together, so we have negative. So we have this one negative. So y star is equal to a over 2 is maximum. So that means we should invest half of the resource during the first period and use the other half in the second period. And that is the optimal policy. And if we want to find the value of V2 of A, we can now plug in y star. So now we have y star is half of A, so we have r over here, half of A, and plus, again, the next one is r, again, half of A. And using the square root formula we are given, so this is going to be twice of the square root a over 2. Or you can say this is going to be root 2 times root a. And you will see this is actually better than the corner solutions. If you look at, if you don't invest anything during the first period, you get root a for the second period. If you invest everything in the first period, you also get root a. And we know that root 2 is approximately 1.4 and is greater than 1. Okay, so we have the maximum profit from these two periods, or maximum return, is root 2 times root a.